State space models look as follows. You have some hidden state, and this hidden state is assumed to have some Markovian dynamics. So let's say this is Z at time, sorry for the small writing, n minus 1, Zn, Zn plus 1, let's say. And then we have some observations which are supposed to depend only on the current hidden state. Now, from the way this model is drawn, you can deduct the important independence assumptions. So let's say that I want to stop at this point here. And I could say that x n plus 2, given everything else, so from the very beginning up to x n plus 1, and the dependence on all the hidden states, that most of these dependencies can be cast away, and this is the same as xn plus 2 conditioned on zn plus 2. And secondly, we have that zn plus 2. Now I can condition on the same thing as above, but really the only thing that matters is the preceding hidden state. And this makes for huge simplifications. So in such models, you often have thousands of these random variables. And now instead of having a conditional probability table with a number of states to the power of a few thousand, you only have these very, very small conditional probability tables for discrete models, or these very compact representations here for the dependence just of the current observation on the current hidden state and the current hidden state on the previous hidden state. So the Z are the hidden states and the X are our observations. Now there are two important classes of such models, namely when your hidden state is discrete, this gives you a so-called hidden Markov model. People use a variety of distributions for the observations conditioned on the hidden state, but the most typical observation models are either a single Gaussian, if you have a continuous observation, or a Gaussian mixture model, or simply the categorical distribution if you have a discrete observation. Now there's often some confusion with respect to the graphical representation of hidden Markov models, which I want to illustrate for the case of an example. I can, on the one hand, draw a transition diagram let's say we want to build an intelligent car, and the car should infer the driver intention. So here's my top view of a car. Again, I'm artistically challenged here. And let's say the car is currently speeding in this direction, and let's say from GPS information we know that there is a bend in the street, and does the driver have any intention of taking this bend, or has he fallen asleep already? Or let's say there is a slower car in front, or a truck in front, and we want to know if the driver has presumably noticed this truck or not, if the driver is going to overtake or not. So in this example, let's say I'm taking just 3 states. Let's say the driver wants to keep going straight, or the driver wants to take a left or a right turn. These are the hidden states. And we want to infer these hidden states from observations, and observations could be, for example, a good one would be if the driver has put out the indicator, or if the driver is what the driver is doing to the steering wheel, and so on. So there are a couple of internal parameters which we can grasp from the sensors in the car. Now, over time, what kind of transitions are possible between these hidden states? So let's say the driver is going straight, and he wants to keep going straight for a while. So this is what this arrow here represents. But then perhaps eventually you want to take a right turn, which will take a while. And from there we want to go back to driving straight, and then perhaps want to take a left turn, which will take a while, and go back to straight. I'm not sure if we go directly from left to right, perhaps not, except on a slalom course. So this would be, what I've drawn here would be a transition diagram. Now, this does not look exactly like the Bayesian networks that we've been drawing. So what's the connection here? Connection is the following. I can draw a Bayesian network. Where actually I have multiple instances of my random variables over time. And well, the random variable, I have only a single hidden random variable. So my random variable, it's just Zn minus 1 going to Zn going to Zn plus 1. However, I would like to somehow also represent these different states, which I've not done so far. So what I could do would be to say my random variable has these states. Let's say S for straight, L for left, R for right. At these different time points. And well, if I am currently in straight, and if I'm keeping in straight, then this would mean that here I was in my random variable was in state S, and my random variable also stayed in state S. And let's say then I went from the state straight to, let's say, the state left. And this is possible at each point in time. So I can go to left here or to left here and so on. But I can also go from straight to right. Sorry. And if I went left, I can keep going left. And if I went right, I can keep going right. And I can go from left back to straight. And from right back to straight. Okay, and it all starts to get a bit messy here. Now, this one here would be called a trellis or lattice diagram. So I have 3 different representations. I have the transition diagram, I have my Bayesian network, and I have this trellis or lattice diagram. They all want to express the same thing. To complete the Bayesian network, I should also add my observations here to really make it a hidden Markov model. Okay, so the goal in such, what are the applications? One application would be to say, all right, so I have these measurements for each point in time, and I want to predict in what state the driver currently is, or in what state the driver is going to be at the next moment in time. Does the driver want to keep going straight or left or right? Now, to specify these conditional probability tables, what we need are parameters. And let's say that we have on the one hand a parameter governing the dependence of Zn on the previous state, and this is given by a transition matrix A. So the transition matrix tells me how likely is it to go from a particular state at the previous time point to a state at the current time point. And now an assumption that's very often made is that these transition matrices are constant over time. So I'm using the same parameter here for all of those transitions. And then I need a second parameter. Sorry, I would have needed a bit more space here. Then I need a second parameter that tells me how my observations are related to the hidden variables. And hence I introduce a variable which I think is often called phi. Yeah, I'm using phi here. And also these probabilities of making a particular observation for a given hidden state, also those are often assumed constant over time. So there is your model. And if all of the parameters in the model are known, the final one that I've omitted is a parameter that tells you the initial distribution over your hidden states at the very beginning of your Markov chain. Once all the parameters are specified, you can try and infer the most likely hidden state given the information that you have. So observed are just the axes, and you want to make a prediction regarding what is the current most likely hidden state, Zn plus 1. Now this is the type of inference problem that we've seen before, and indeed you can use message passing here. And well, this was this algorithm, it's a fundamental algorithm. This was invented long before graphical models and message passing were known. So it got its own name at the time, and the messages in this particular system here are called, or the way of computing them are called alpha and beta recursions, which are the messages that you propagate from the back to the front and from the front to the back respectively. But often enough, these parameters are not known, and then you need to use the expectation maximization algorithm for parameter estimation. Or you could use something else, but EM is the most typical one. So in that case, you would want to find A and phi and the initial probabilities for your hidden state. And since we have some missing values here, using EM, we can estimate them in the E step, and then in the M step find the parameters that give the greatest likelihood to those, and keep iterating that. So this is, what was it, 5-minute summary of the hidden Markov model. Where it really became big was in speech recognition, and it still is an element of most speech recognition systems. There, the idea is the following. If we have an utterance, we could, let's say we train different Markov, different HMMs which recognize, let's say that we have a hidden Markov model which recognizes the word one, and we have a hidden Markov model which recognizes the word two. And we can then compute the probability of a given utterance. So I'm trying to sketch an amplitude here, so something that was recorded by microphone under this model 1, and I can compute the same, the probability of the same amplitude under the model 2, and I can then compare these posterior probabilities. Maybe I should say given here. I can then compare these posterior probabilities, and the model which gave the greater likelihood to my utterance is the one that I think is the best fit. So if I get a greater probability from this one than from that one, then I would believe that the person has been saying one and not two. And also in speech recognition, by the way, this is where these arrows are important, because people, well, they, some people speak very quickly, others speak slowly. So, but you want to be able to use the same model. And this is why you can allow the model to stay in the same, let's say in the same phoneme for an extended amount of time if necessary. However, if you just use this mechanism, you have an exponentially decaying state distribution. So you see, if I have a 0.9 probability of staying in the state straight, then in the next time step, now without any observations, I have 0.9 times 0.9 probability of still being in the same state, and at another, if I want to stay in there even longer, it's 0.9 to the third power, and so on. So you have an exponentially decaying state length probability. And hence there are a couple of models, if you have a better idea of what the state length should be, that incorporate that more explicitly. Now the second important class of models is when this type, when the hidden state is continuous, and people make, if you make further simplifying assumptions, you get out something called the Kalman filter. So there you have a Gaussian hidden state, and you have a linear transition model. So your new hidden state must be some linear function of your old or your previous hidden state. And you also have a Gaussian observation model. So the current observation, given the current hidden state, is going to have a Gaussian distribution. So I could write that as the hidden state at times n must be some matrix multiplication times the hidden state at the previous step, plus we admit some Gaussian noise here. Gaussian observation model means that our current observation xn must be some linear function of the current hidden state zn plus some noise, which also is assumed to be Gaussian. And the initial state is also assumed to have been a Gaussian, centered around some vector mu0. Okay, if we start with the Gaussian and then we transform it linearly, we have a Gaussian, and if we add Gaussian noise, it still is Gaussian, and our observations are a linear function of a Gaussian plus a Gaussian. So everything is Gaussian and linear, okay? This is bottom line. Now that sounds like a very simple model. Why would you make those strong assumptions? This is for the reason of tractability. So you want to also pass messages, but this time the messages are continuous. And I said before that when you have a large label space, your messages are going to be big vectors and cumbersome to handle. And now our messages are no longer vectors, but they're entire distributions. So they're continuous distributions. And the only way to deal with such continuous distributions efficiently is to make, well, strong modeling assumptions. In particular here, if everything is Gaussian, then it is enough to let a message consist of just the current location and the current covariance matrix. So I need just a vector and a matrix to parameterize this continuous distribution. This is one reason, and the other reason is that the prediction and the updating steps, so the marginalization operations, that they are analytically tractable. So we have tractability both of the marginalization operations. So before we were summing out when we were talking about discrete variables, but now we integrate out, and it's important to have this marginalization tractable. And then we also want the actual messages to be compact. Now, these are very restrictive assumptions. Does it still make sense to use this model? Actually, in an interesting variety of situations, yes, it does. The most famous one being tracking. So some people say that this is what made human space flight possible, and it was invented just in time in the 60s. And before Kalman invented this, well, people used, or before these, equations for the message passing, which was not called yet that at the time. So before the simple model was set up and before these message passing equations were found, people tried using much more difficult mathematical models and ran into problems. Now, this type of system with the Markovian assumption and here being fully linear, it is well adapted to modeling Newtonian systems. So this is, for example, useful for stellar dynamics, where in stars I now also include human-built satellites, missiles, spaceships, and all that. Because in Newtonian dynamics, indeed, the current state only depends on the current state only depends on the previous state, and your hidden state in such an example would, for example, be the position and the velocity, and if you want, you can go to higher orders, acceleration, and so on. And then you know that your new position is going to be the old position plus velocity times time step, and so on. Now the limits of this kind of approach is that it's good for tracking a single object which follows Markovian dynamics, which in particular does not split, and so on. And if you want to look at if you want to track more complicated systems, systems that can divide, systems that do have nonlinear dynamics, you need to resort to other models, like Bernhard is working on, and that he can tell you all about. And we will, at the very end of the semester, which is starting to be near now, we will look at such models and how they can be trained, and how inference can be done under such models. You have a question? Yeah, you can, so you're asking about what if you have multiple planets? You need to increase your state space. So you need the position and velocity, you need the position velocity of all planets in the system. So let's say we have, two objects orbiting around each other. Then you would have a position P1 and velocity V1 for the first one, position P2 and velocity V2 for the second one. And that I could now add an index here. We're looking at this at current time t. And now we have a transition matrix times the previous one. And so on. Okay, and now I am going to experience, so let's say I'm going to experience an acceleration which depends on, I think I need to include accelerations also. Then your first object will experience an acceleration that depends on the current distance from the second one. And over time, yes, you're discretizing over time. But yeah, yeah. So the even the you know, the gravitational potential here, it's not a linear function of distance. So this is, you're right, where you already run into problems, and then you need to linearize your system. And there are a couple of extensions, for example, the scented Kalman filter, where you do such things, where you linearize. So you're right, stellar is not good. Let me call this satellite. Then our satellite is infinitely much lighter than.
Correct your prediction for dimensions again.
Yeah.
As your error will increase and the simulation will break down for scatter dynamics, but they are updated by the measurements.
Yeah.
I think if you make it fine-grained enough,
Yeah.
no problem.
So Bernhard is saying if you have sufficiently dense measurements in time, you can correct for, you know, the errors in your model. But you know, the model in itself, as you have shown, is just wrong for if you really have, you know, objects of similar mass. Okay. Nevertheless, people have used this for tracking single objects, you know, for tracking planes and such. And planes are not, you know, they're only linear to some extent, because at some point the pilots fly curves and so on. And this is where the measurements come in. And well, something that you can study nicely in Kalman filters is, so if you now go through all the math and what the messages look like, then again, qualitatively, it looks like this. Let's say we have some initial velocity and some initial uncertainty in our position. You know, let's say it is heading in this way. Then over time, if we make no measurement, your system becomes ever more. The location becomes ever less precise. So here this is now a linear extrapolation, and I'm trying to indicate here with these isocontrolized the density of the Gaussian that I have. And let's say at this point you make a new measurement, and let's say you have a sensor whose resolution in azimuth is much better than in what's the other one? Elevation. So let's say we have a sensor that gives you a measurement which also has Gaussian noise, but the noise is much bigger in the y than in the x direction here. So this would be a measurement or an observation, and this would be your prediction. And now these are two Gaussians, and hence if you now do the update step, so to compute z n plus 1 given z n and x n, you get integrals and so on, which give you another Gaussian. And in this particular case, you would get, as a result, let me do this in green, you know, this Gaussian times that Gaussian, you would obtain something that is probably located here. So you would have your measurement would have specified you the x position, but wouldn't have said much about the y position. You marry this with your prediction, and now you start over. Okay, so this was just qualitatively. As I said, this is just passing of messages along this very simple structure, which you need to do. And this was one of the nice findings of of this whole framework of graphical models, that models which had previously been invented in totally different areas, that they could be summarized very compactly, and that all the math that was previously developed for those models could be reduced to just passing messages on these simple graphs.